Morning Year 13. In this weekly review we're going to go through the basics of the binary and the linear search algorithm before looking at the homework questions. So to begin, you can see them on screen. There's the linear search and the binary search. We'll look at the mechanics of both. When talking about the linear search, make sure you mention that there's generally implemented with a flag, a boolean value that allows us to flip if an element has been found or not found. Next comes an iteration, and we iterate or traverse through the length of a data set. Third is the comparison. We're looking at each element and comparing against the search criteria or the value we want. And final is the return. We're returning either found or not found, or a rogue value to allow us to break out or make a selection if the value is found or not. Then we need to look at the efficiency of the linear search algorithm, and we know that when we're searching, the worst case is what we call O to the n. It's very poor efficiency. If there's a million elements, the worst case is that we have to make a million operations before we find it. Best case, it's one operation at the start of the array. But we do evaluate algorithms with regards to the worst case scenario. So it's what we call an O to the n, a big O to the n. However, when we talk about the linear search and its use of memory, it's O to the 1. It has got constant use of memory. That algorithm that you see on screen does not require any additional memory. If I've got 10 elements in an array, or if I've got 10 billion elements in an array, the memory is still the same. It just takes longer to search. So next we're looking at the binary search algorithm. At A2 you'll start to see we're looking at an iterative implementation. GCSE, not an iterative, we're looking at a recursive. GCSE, we looked at an iterative. So the first thing you talk about with the binary search algorithm is the concept of the midpoint, and you know that that is the lower bound plus the upper bound, floor divided by 2, and that gives us the element to make a comparison. So we look at the data set's midpoint and make a comparison, and you can see that this recursive implementation, recursion is a function that makes a call to itself. It also is something called a base case, generally an if statement that allows us to break out of the recursive call. So this algorithm is calculating a midpoint. If the element we're looking at is the midpoint, we break out, we found it. Else, look what happens. If it's less than, call the function again, call the recursive function again, only split the array from the beginning to the midpoint value. If it's greater than, split it, increment the midpoint and call the function again from the midpoint plus 1 till the end of the array. So study the recursive implementation and make sure that you can recognize it. Function making a function call to itself. That is called binary search, and you can see in the two statements it makes a call to itself. Finally, the efficiency of the binary search algorithm. You should be able to say that it is O to the log n in base 2. So for example, if there's 8 elements in a data set, the worst case scenario is 3. 2 to the 3 equals 8. If there's 16 elements in our set, worst case scenario is 4. 2 to the 4 is 16. Memory is the same. If it's a recursive implementation, each recursive call requires the function to be placed in memory. So if there's 8 elements, I'm going to call the recursive function 3 times. If there's 16, I'm going to call it 4 times. If there's 32, 5, and so on and so on. So you can see that the memory requirements of a recursive algorithm grows. And again, it will grow at log n in base 2. So that's the mechanics. Now we can move on and look at the homework answers, which again are basically covered in that. So all I'm highlighting here is the mark points that I was marking in your work, that when you're describing a linear search algorithm, a mark point if you said there was talked about a flag, there was a mark point if you talked about iteration, and a mark point for comparison, and then a mark point for the return. You only needed 3 of those for a maximum of 3 marks. Next, question B was the one that was generally answered poorly. It says, how could, if it was the data was sorted, how could we improve the efficiency? Now if you think about it, if the elements in the array like you see on screen are sorted and I'm looking for the number 10, I'm going to make my comparison at the first element. Does that equal 10? No. Is it greater than 10? No. Go on to the next one. Does that equal 10? No. Is it greater than 10? No. And so on until I get here. Does that equal 10? No. Is it greater than 10? Yes. And that could throw up a flag to break out in the array. So if you were looking at it and you said only iterate and compare until the value or one greater than it is found, you'd get the 2 marks. Or even if you give it programmatically and you said, if there was an elif statement or a part to the case select, if the array element is greater than the search value, some type of break. Or if you said while the search value is less than the array I and not found. So even some type of pseudocode or programmatic implementation, you would have got the 2 marks if there was 2 parts to it. And next part, pretty straightforward. 1, 3 and 7 we were looking for there. The binary search, need to calculate that. Well, we know how many elements, not 1, 2, 3, 4, 5, 6. In the first probe we're going to be 0 plus 6 floor divided by 2 is going to give me 3. Element 3 is 15. 7 is less than 15, so I've got 0 and 2 being my upper and lower bounds. Floor divide that. Element 1 is 3, and then I'm left with 7. So 15, 3 and 7 for our mark points. And then when we look at the advantages and disadvantages, 3 advantages. There's only 2 mark question, but any of these 3, if you said it was easy to implement programmatically, it's memory efficient in comparison to the binary search, and if you said that it's O to the 1 or it's constant memory, and it works on unsorted data, fine. And then the downside, if you mentioned the binary search, downside, it's inefficient, and the worst case is O to the N, or if you said it was the last element in the set. So there's plenty of mark points available there, and I think everyone grasped that. And that, folks, is our search algorithms. There is no work set for midterm. We meet again on the Monday that we're back. Have a great break, and we chat week after midterm.